Okay. Hello, everyone. So today, Aziz Kharoof from the University of Haifa. Well, starting from next week from University of Bilkent University. So he's going to tell us about extending and gluing simplicial distributions. So these are important techniques. And then we will see later on in the upcoming weeks how they're going to be useful for proving fundamental results. So Aziz, you can take away.
Thank you, Jihan. Thank you. Hi, everyone. Yeah, so let's actually start because we already something like 5 talks before about simplicial distribution. But maybe let me start from this point that let's call it the map of contextuality, the map that defined from, if we have a scenario, like let's say a given scenario X, Y, okay, a measurement space and outcome space. So we actually here is all the simplicial distribution, right? So we have this map that I think like from the first talk Jihan defined that theta x y from the distribution on all the simplicial map from x to y to the simplicial distribution, okay? This map. So let me remind you the formula for this map. So if we have here, like, let's say P some distribution on the maps here from x to y, we call it section. So this will go to theta. Okay, let's call it theta. But this is depend on x, y. I will explain this also later. But this will be distribution here. So what that means? That means a map, simplicial distribution. That means a simplicial map from x to dy. So how it's defined? How it's defined like in for simplex here. If I take simplex, like we know that a map from here, it's some maps for every degree. So let's say for degree for x in xn. So we have then here, this will be a distribution on yn, right? But how it's defined, just give the formula, and then I want to say something. To remind you the formula, because the formula given before, in the first, I remember in the first talk. So the formula of this is a distribution here. So what it's even for y, it's what is the number here? Like it's supposed to be number between 0 and 1 for every y and yn. So this we take the sum over all the phi. Here it's p big, I mean, right? Okay, so maybe I would write even, okay, p, but big I want because same p from here. So we will actually take all p of some phi. Where is phi? Phi in like a simplicial map from x to y, such that phi of x give me y. Okay, phi of x it's equal to y. Usually we write it even I will write in the same symbols that Jihan. Instead of writing nx here, we writing x down. Okay, yeah. So it's better to write the same. Okay, so here x and here y. Okay, so this is the formula. And one can see from the formula that it's natural. Okay, the formula, it's natural. What I mean by natural, I mean that it's not depend on what it's y and what is x, right? It's not depend, like it's we like usually for y we said in the we use, for example, y to be delta of z2, delta of zm in general, or we use sometimes the nerve of, right? And maybe one can use something else. But we said like here is a formula, we didn't say like, okay, if we have this y, then it's something else. If we have this y, then this is the formula. No, it's it's something general for every y and for every x also, the measurement space. So actually, how people define naturality, let me like say something about naturality for someone who don't know what we mean by naturality, like a precise definition. Because actually what we have here, there is a functor into, like this, is a functor in two variables, x and y, right? Like we put here two simplicial sets, and this give me a set or convex set, actually, right? And here we have another functor, right, from xy. So this is actually like a map between these two functors. So like that it's not also like for every xy, for every two object, but it's how we can see the things that it's really natural, what I explained, that not depend on xy. We see this through maps. Like, okay, this is a part of category theory, that we have also map. We define through maps. So we can define this naturality through maps. What does that mean, through maps? That if we have, if, okay, if we have, let's say by the variable x, if we have a map from x to x1 to x2, I don't want to use x1, x2, maybe I will use xw or something like this. Okay, if we have a map from x or to x tilde, okay, like map like this f, then actually this will give me, this will induce a map from x tilde to this, okay? How this map defined, one can imagine. Like this is a functor, okay, functoriality, because actually like we have here phi, for example, what is phi? Phi from x tilde to y, and we can compose it with f, right? F, and then this will be from x to y. So we have a map like this. Also, we can do the same for simplicial distribution. Okay. We call this map because it's coming from the map F. We will call the F star like this up. Okay, F star. So we have here also F star. It has the same formula here actually, because also here we have a map from x to dy. But then in order to get the map from x tilde from to xy, to get this, we will compose with phi, with the f, sorry, this, and to get a new simplicial distribution, okay? So the same formula we have. This induces this, but also we can apply here, of course, like I will, okay, sorry, I will remove this. I want to write something. So here we can apply also D on both of this. So if I apply D on this, I can apply, we say that this is the distribution functor, right? So we can apply on the map. And then actually, yes, the F is good. Then we have theta from here to here, right? The theta of x tilde y. And we have this, the one for xy, right? So actually this diagram is commutative for every F. Yeah, if we have this, then we say nothing about this F, okay? Like any simplicial map. I mean, always like simplicial map, of course. I mean, always simplicial map, we are. Yeah. So if we have simplicial map like this, then we get this diagram, okay? So that's what I meant by the natural. This is how the naturality defined. This is how people define naturality in the variable of x. Like it's not depend what is x. The formula up, we can back and see that the formula, it's not depend on x. So, and we can do the same if I have a map from y to y tilde. Let's call it G. Then we have similar, okay, let me write it fastly. So x, like fix x, but now y, but this actually will give me this map. One can try to explain to himself why it's give me this map with the same order. Yeah, we compose again with CG, but which side we compose, so that's why it's the same order. Usually people use this because this map G induced from this map G, and we can apply the distribution monad on this. On the other hand, we can do the same for simplicial distribution. X. Maybe now we apply D also on G, and then we apply, to be honest, actually what we're doing here, we apply D on G, and then we doing this. If we want to be really like precise, to X, D, Y prime. And really this also diagram commute, okay? This diagram also commute, like going by this and this is the same as to compose these two functions. Here, theta, x, y, and here, x, y, del, okay? So this exactly is this is the naturality. So again, I want to back why this map is important in the theory of simplicial distribution, because this we define contextuality using this, yeah? Like everything in the image of this map, every simplicial distribution that in the image of this is contextual, okay? But the good thing that this is natural, and we have we can have from a map this square, okay? Of course, we can have, we will talk about this later, like if we have not only a map, a diagram, so we will get here a bigger diagram. We'll talk about this, but okay, see why is this helpful, okay? Why is this helpful? This this observation, why it's helpful, or this property of the map theta. Let's say we have, let's going, I will actually I will focus in this one. In this talk we will focus, we will use the second situation later, but let us focus in this talk, we will focus in this situation. Okay, we will in the situation when we change the x, like we focus on the naturality of x. This is the naturality of x, on the naturality on the x variable, yeah, on this kind of naturality. Is this talk? So why it's helpful? Maybe I can do like this. Can take all of this to me with me. Yeah. Yeah. Oh, what I was teaching before, so this is from what I was teaching, but why it's now, why I can't do copy paste? I did copy paste now. It's funny. Yeah, just a minute. Yeah, it should be that I can do this again. I will do copy now. Now. Okay. Okay, we have theta here for xy and theta here, and the diagram commute. What it's helpful that the diagram commute here, what we can get from this. Here theta and here theta, the one is, like if we have some distribution here, we have one distribution, let's say P here. And let's say this is coming from some distribution up. Like let's say here there is a P and there is some Q, which is applying F on P. Okay. So if we know, let's say that we know that this is not contextual. Let's say that this is not, we know that this is not contextual. So what did that mean? That means that we have three images of this, right? That going by theta to this. So we have, let's call it Q, big Q axis, okay? But we know that the diagram commute, so going like this is the same as going like this, so we can go by this to some prime, and by theta going to this, so that means that Q is also non-conceptual. So this is so easy, but this is really helpful in many cases, and we use this. So let's write this proposition. Given f from x to x tilde, if p in simplicial distribution xy is non-contextual, then this, it's like it's the push forward of f, it's called, like in there we call this push forward of it. So this one push forward by f is this distribution that it's here in x. One of this is with tilde, yeah, this one. Okay. So this one is also non-contextual. Okay. So this is a property we have. Other things like corollary from this can be when we have this situation.
Oh, wait, Aziz, did you need
Yes.
EYs in the target on the upper diagram?
Mm,
Oh, no, you wrote simplicial distributions. Sorry. Okay.
yeah.
Okay.
And now we have another important situation when this everything, like here everything is now I know why there is no tilde. It's when I made this copy paste. If this is surjective, what it's mean like this is surjective? It's mean like every distribution here is non-contextual. It's mean like this scenario is a classic. These scenarios are x tilde y is a classic scenario. There is no this phenomena of contextuality. Okay, every simplicial distribution is coming from some global distribution. So that's what I mean. If this is okay, if this is the case, and then we can say that something, if I have something that extending from here, everything extending from here is non-conceptual, right? Then in this case, we can write proposition again. So they're given f from x to x tilde, if or suppose that x tilde y is a classic. What I mean by, okay, maybe we don't use this in our paper, this name, but we know what that means. That means it's this one is surjective. This is what I mean by this classic. That's a map theta is surjective. I wanted to change that. Yeah. Okay. Then if this is classic, then if this actually corollary from what we said before, right? It's even not a new proposition. It's only corollary. If P in here is in the image of F star, then this P is non-contextual. And this can be even if and only if also we have that this is also surjective. So if in addition, okay, maybe let's add here, if in addition, f star from simplicial set x, y, this is surjective, like what is the case? I mean, again, maybe I can write it here. Again, in the case that both are surjectives now. Sorry, just a minute. Let's say this here is surjective, and this is surjective because we applying D. If we applying D on surjective, this will be surjective because it's on sets. Okay, one can see this property. But if this is surjective and this one is surjective, then we have also the opposite side, yeah, the inverse direction. Okay. So what we said before that if we have something here that coming from up, then it's non-contextual because this is surjective, we can go like this. But the opposite is true. If we have here something that it's non-contextual, like coming from something here, and this is surjective, that means like this coming from something from here, then that means that this is extended because like going like this and going like this is the same. Yeah. So let's write it if and only if now. Now we can write that it's if and only if. So let maybe back to what we wrote before, and maybe we can copy paste what we wrote before and write it if and only if. I think it's not good because it's yeah. Okay, let's write it here. Then P inside this lies in image if this if and only if P is non-convex. Okay. So this is what we have. Usually we use this when the map from X, this map, what we have X from, it's inclusion map, okay? So I will show now some example. Usually we use this when F is an inclusion map. Like some inclusion, I will show now example. What we have the map we said from X to X tilde. Like because sometimes we can include some space on some bigger space, which is a classic. What we mean by classic that there is no non-contextual. I will show. Okay, we always doing this because it's the easiest non-trivial example. Just the cycle or the what CHSH scenario. What's called we. Let's me remind you. I will do this there. So here example. Let's say that we have this simplicial set. You know what I mean. Okay, of course, simplicial set we say, but this is like we talked about this. Okay, this is like the regularization of this or how what is represent geometrically, what is represent. and with delta z2, let's say or even delta zm, why not? Yeah, with anything here, delta zm, and any y can be, but I want this to represent, in the case of z2, is represent the CHSH scenario. So here, actually, we know that this one is, if we take this one, two triangle. So this one included in this, right? This one up is included in this. Okay. Yeah. So we have this map, right? The inclusion map, it's obvious. We have this map. Then we have this diagram, but actually, first of all, let's be sure about the last corollary. I want to use the last corollary, which with F and only F, but let's be sure about the surjectivity of the map. First of all, this is a classic, like this is always, when we have this, okay, I will prove later why this is a classic. Okay, we will prove later, not now. In this class, actually, in this talk, we'll prove that this is classic scenario. Like what I mean, the theta, the corresponding to this is surjective. Okay, we will prove later in this talk. By the way, it will be a good exercise to prove by himself why really everything is surjective. Anyway, what we need also, we need to show that this map, the inclusion map, actually, it's give us a map from, let's call its map, let's say I. So this map actually give me a map from simplicial set on this one, two triangles, delta z2 or m to this one. This, we want to show that this is surjective. In fact, this is even isomorphism. Yeah, this is isomorphism. How we can explain this? It's more than surjective, it's even like injective also. But why this is true? Because a map from any x to delta zm determined by let's say what's called the map phi. It's determined by phi 0. What I mean by phi 0, like values on the edge, on vertices. Yeah, phi 0 from I mean phi 0 from x0 to zm. It's defined by this. This is the determinant. One can also, it will be a good exercise to prove it, or to check that it's true. Yeah. So that's why actually they have the same vertices here, right? We see like the vertices here, we have 4 vertices. This determined any map from here, so it's determined only by the vertices. So it's the same maps here we have here. Okay, so we have this. Like what we have actually, we have something like this. If we have a distribution, we already have some how to write distribution here. Okay, let me maybe write some general distribution on this. We say like we have B00, B101, B10, B011, like a box, right? And here, because there is a point between them, so this give me the non-signaling, right? Because such here, so it's mean, we said this before, like it means that the, okay, let me write it and then we can, here another Q0, okay, yeah. It's the same distribution, I mean, by here. Or maybe I will write here sigma 1, sigma 2, and then the same P I will write, yeah, here all for sigma 1. And here all for sigma 2, so the same P. Okay, let's say this is distribution. P1, P1, 0, and here, and here. So this distribution actually is non-contextual if and only if we can fill this distribution here. We can fill its to distribution here and distribution here, such that when we restrict it on this, we will get this one. When we restrict it here, we get this one. Yeah. So something interesting. This is some characterization of contextuality that we will use later. We'll use later. Let me just say how it looks like distribution on here on some distribution. Let's call this tau, for example. So how it's look like a distribution on tau. Let's say like this is a distribution that extends this P. Okay. We want actually at the end we want Q in order to in order to be sure that this is non-contextual, because it's if and only if, okay, it's we need that the Q on here to be equal to P, right? On this one to be equal to P. So how it's look like a distribution on tau on some triangle? One can write it like this, like there is one additional dimension. Yeah, one can write it like this: Q 0 0 0 Q. Sorry. Q0 1 0 Q1 0 0. This is when the last one is 0, all of them. And here we can write when the all of them it's 1. The last one is 1. The same. It's the last one. 1 0 1 1 Q1 0 1 Q1 1 1. Okay. This is like this, like it's not yeah, like two matrices like this. It's okay, I will write it maybe. Yeah, there is some cube like in dimension, like something like this. One can write. Okay, so but actually here, and this maybe we can see why it's good sometimes to go to nerve instead of using this delta Zm. If we take the same, now I want to take the same example, but to represent this when I use nerve. So let me now give this example. Now it's also represents the CH-SH scenario, because, okay, I want to back again to what I had before, just to remind you something like here. What is the CH-SH? When we have two observer and everyone have one measurement, right? So that's why we used here this. So when we use delta Zm, the measurement for us is vertices. So we have here the measurement for Alice is A, and let's say A prime, and the measurement of Bob, it's B and B prime. He have also two measurements. You see what I'm writing, because I'm going up. Maybe Salman stay. I will put here all eyes on me in order to. You can go up.
I see what you're doing. Yeah.
Oh, you see. Okay. You are. Yeah. Okay. So we can. So what we have actually, like here we have context, right? So context is an edge here between, but the only thing that the measurement here are the measurement. It's not important the direction. It's the same, but the importance that the measurement is the vertices here in this case. But when we go to the nerve, the measurement will be the edges. This is the things. But okay, what it's why it's good. So let me show here that actually this is our first example. What Jihan start with the torus. Okay, so here when we actually use with nerve of Z, I will take here 2, not M, general M. I will say Y. I will say later Y. Okay, let's see here. So we have this A, and we have B with A. Okay, and then this is a context. Here, the context will be triangle or something else. Depends how many measurements. If we have 3, like we can choose something. So we have this. And this also, we know that there is a context with P prime. So we have this. And we have here let's say A prime with B. And we have this with P prime again. So there is 4 contexts, but the contexts are triangles. And we now take this with this. No, I wrote wrong. Okay. Yeah, I want to take it here. Sorry. Thought I could with Charlotte. No. Okay, anyway, it's like this. And here B. Here's the same B. This one, the same B. Like this is a copy of this. So one can imagine, like if we glue this with it, because this is the same one. So it's this will be glue with this, and this will be glue with this. So imagine what we have here. If we glue this with this and glue this with this, actually this will be like here where I have this, and I glue this too. And then I have this will be circle here, and this will be circle here, and I glue them together. I will get what's called torus. But this torus is actually have here nothing in the middle, so it's puncture torus. Okay, this is the puncture torus, and this will be our outcomes, our measurement space, and the nerve of Z2 will be our outcome space. Okay, who wrote this? Anyway.
Sorry, it's me.
Yeah, okay. It's happened to me all the time in the classes, but now it's okay. At the beginning, it's so every student was writing. Okay, this example. So let's see why this example. This okay again. This represented the same scenario we defined before, but with because here the outcome changed. So we can actually include this one also. We can include this one when we cover this hole, this in the middle, we cover it, okay? We cover it and get the torus, like when we cover it by this, like this, yeah. We cover it and we got here a torus with some direction. I don't know, like here this is the direction. It's like this, right? Like this. Okay, anyway, one can, okay, as exercise, do the direction. So this is the torus and this is the puncture torus. And here, really, one can check that we have this situation, what we say, that this, first of all, is the classic, okay? I remember, first of all, Salman, like, checked this for us in computer, and then it's proven in other paper for Salman, Jihan Ladhoyo. They prove that this is a classic with, this is with nerve of Z2 as the outcome, because if we take nerve of Zm, it's not sure. I'm not sure. Did you check this? I'm not sure that's classic. I think no, it's not classic. And we can say why it's not classic for Z2 for something else, but for nerve of Z2 with nerve is a classic. Okay, the classic scenario. This one with outcome space nerve is classic, And here also one can show that we have this surjectivity with the sections, the map of simplicial sets. So we get the same, like, again, like some distribution here on the puncture torus. It's non-conceptual if and only if it's extended to the torus, okay? So let me write it like this proposition, it's important. Simplicial distribution on the torus. Torus, it's like this. I'm afraid to write torus because it's which 2U or like this. I don't remember. Yeah. Okay. On the torus or in the puncture torus, sorry. On the puncture torus. Torus is non-contextual if and only if and only if it is extended to the torus. Okay, here we mean again, we mean when the outcome space is a nerve of Z2. Okay, it's important. Now, why this is good? What is the difference between the first example and the second example? Because it's both, okay, even it's easier like to prove that this is non-contextual in the first example, which is both are represent the same things as we said. Okay, let me make it this from far, we can see maybe both or something. Okay, in the first example, we have this, and it's easy to prove that this is non like mathematically, not by computer, to prove that this is a classic. And even it's work for every m, But in the second one, it's work only for 2, and it's not easy. It's, Jihan and Salman know it's very good that it's not easy to prove that this is a classic, even for Z2. But why this is good? Actually, this is good because we see something very important here, that actually when we cover this, it's like at the end, like this extended, it's depend on the value of this, the distribution on this edge. You see which edge I am, yeah? I'm doing you with hand. Again, I want to take this, or yeah, sorry. Like we see that this is covered because it depends, like let's say we have some distribution here. We have some distribution here, like here P, some distribution. So here we have some numbers, here we have, but then actually the like what we said here, like the what it's called, the condition to be extended is depend only on the value of this on these edges. Yeah. This edges, by the way, it's like it's not from the first story. The first story talking about A and B. This and this are the measurement, and this is like new edges, like not represented any measurement, right? But because we use the nerve, so we still have this, and here this extending, the extension of this, it depends on these edges, yeah. And this can also tell us that the Bell inequality will be depend on these edges. You remember that we defined in general Bell inequality, and we said it's some linear equation that something like this, P sigma here, which sigma is some simplex, and up it's Y, right? Or 0, yeah. So when Y it's in that it's depend what is the simplex, like in something like this, yeah. And some mere coefficient, don't remember what we called it, beta and plus something like this. But here we can know, one can from this directly say that the Bell inequality, sorry, for this scenario can be described using these edges. Like these edges only will appear. We can describe with other edges all the time. We can change and describe, but there is some representation of the Bell inequality that use only these edges, right? Why? Because we see that the extending depend only on these edges, on the value of distribution on these edges, and as the corollary before told us that this is non-contextual if and only if it's extended. Okay, so really this is can be a good in order to find Bell inequality or give its topological meaning or geometrical meaning as we see here. Okay, like even something like some simple corollary we can see without finding the Bell inequality, only that it's depend on this edge we can see easily using by moving to the nerve. We don't see this in the previous one. We don't see these edges here. Okay, we don't see this distribution on the edges in this representation. Okay, so now actually we move to applying this theta on diagrams because we say that it's natural map this theta, so we can apply this not only on one map, we can for diagrams. So it will be good when we doing this for push out, because sometimes like we have some measurement space, like let's say here measurement space X, but this measurement space X, it's coming by gluing to other measurement spaces, okay, like A and B here, okay, through some through some C, let's say. Okay. This is push out. Okay, how I can explain it, like mathematically, like if some have some disk, this is the C, and we have here suspension of this. Let's say this is, okay, sorry. Like let's say this is A, this is C, and this is another B, and here we have inclusions. Then we get, for example, this suspension. This is cone, and we got here some suspensions. Okay. So this by gluing this. So this is what we mean by push out. We don't have the time to, who don't know this, we don't have the time really to define precisely now. But this is what we mean when we have like, or we have like even a circle, like we can get this, and here 2 points. And we glue through this. We glue through this. Here, this is inside here. And then we get this circle. Okay. Yeah. So this is example. In this case, if we have simplicial sets like this, let's say given this diagram, push out. Okay, okay, this is push out in simplicial sets. All of them simplicial sets. Then by applying this naturality, what we get actually by applying this naturality, like for every map, we will get square, right? For every map, we will get square. But in general, let's maybe do it simpler. If we applying first of all simplicial distribution, then we get this. Remember that it's will be like contravariant, so it will be like this. A, Y. Yeah, you see, everything replaced. And we can also do the same thing for simplicial, when we apply the simplicial this functor, like this functor, I'm applying on all of this. Okay, so this contravariant functor, so we will get this. Of course, we apply D on all of them, distribution. And we have theta from everyone to everyone, like this theta. Maybe let me change that, it will be easier. Yeah, here I mean theta for AY, here theta for XY, here theta for, yeah. And so what we did here, why we get, for example, why we get, first of all, sorry, this one, because of the neutrality of theta. But why it's good? Because actually maybe this one will be hard to understand when some distribution here is non-contextual or contextual or something like this. But maybe because I didn't say this, I will say like we can go to here, and maybe by this we can know if this is a non-contextual or not. But actually here is important fact that this will be pullback here. Like if we apply simplicial distribution, because actually it's coming from what is this functor simplicial distribution? It's actually this one. Like we apply this one. So it's some general fact like this. If we have here inside pushout, this will be pullback, something general. Okay, so this will be pullback. What it mean pullback? Pullback, it's like generalization of product. Like when you have a product, like let's say you have two sets. Let's say what I used all. Oh, okay, U and V. The product of U and V. Okay, everything's here. It's someone from here and someone from here. But if you have like this diagram, let's say here, anything's like W. Okay, so the pullback of this, like when I have two pair U and V, one here, that they are agree on W. Okay, this all the elements like this give me what called the pullback of U and V. Okay, so this is the pullback. So this is very good. Like every distribution here actually it's determined uniquely by when we going to like restricting in on A. Why I saying restricting? Because usually we'll take these diagrams to be inclusions. Usually we take these ones to be inclusions, like here inclusion, here inclusion. C also included in this, like push out like this usually we use. So when we restrict it on A, and when we restrict on B, yeah. So now I want to know if this coming from something here or not, if it's have some joint distribution or not, non-contextual or not. So we can ask about these ones and play by diagrams. Yeah. This is like a chasing diagram, it's called it. So in classic homological algebra, it's something so familiar people do. I did my mastering in classic homological algebra, so that's why I like these things. Yeah. So you see, like when we go, let's say that this one have Q here, and this one have Q prime here, and we ask how can this actually help me to get someone here? Yeah. So maybe one can say, okay, maybe this one agree here, but maybe not. Okay, this agree here. We know that this agree here because it's coming from the first one, so this agree on it's here, it's okay. But this one, we are not sure that they are agree. I will give examples. Okay, let's say that this is agree here. Let's say that we can find some pre-image of this and some pre-image of this that agree here, let's say, okay? If we can find, okay, it's not also ensuring me that we have someone here because it's not a pullback. This square, it's not a pullback. This is not a pullback square. Because in pullback, we mean when we have pairs that agree on the intersection, then that means that it's coming from, it's represent someone here uniquely. This is a pullback. But actually, it's a weak pullback. This one is what called the weak pullback. What it's mean weak pullback? Like weak pullback, it's mean, okay, if you have someone here and someone here that agree here, so you have, it's coming from someone here, but maybe not unique. There is money maybe, but it's good. It's enough for us. It's enough for us to have someone here. Let's say what we call, maybe I should call this Q1, Q2, it's better. And then if they are agree, then I will get some Q here. And one can prove that this one, because the image of this is this and the image of this is this part, so the image of this will be this P. Okay? So this is what it's called the gluing lemma. But we should actually, now we will write it like formally, but before this, we need also, or maybe we will write formally and then we need to prove, really, I want to explain to you why this is a weak pullback here square, this one, okay? That's what I need to explain to you. Okay, let me write the gluing lemma. And then we go this, okay? Lemma. Again, given pushout, or even you can think about this as inclusion and this is anyway. Okay, pushout of like this, what we put before. Oh, sorry. Oh, I'm almost like with this new version, maybe 3 weeks I'm teaching with this version. I'm not good with this. Like here, what we said, A, B, and here X. Let's say this is a push out, as we said later, before, sorry. And the area inclusions, it can be not inclusion. And then we have, then if, what I want to say, for P simplicial distribution on X, this is the important thing with us. We want to understand the simplicial distribution here, if it's contextual or non-contextual. Okay, P here. P is non-contextual if and only if there is Q1 in here for A and Q2 for B, such that first of all, we need this to be pre-images by theta to the restriction. to A and B, which is form actually this one and this one form the P, right? By knowing this, we know what is P, but also we ask this to be the same on like Q, maybe how I can say this, a Q1 and Q2 agreed on, or maybe we can say when we restrict to, when we go to here, because it's not really restriction, but anyway, to see like the intersection between them, okay? This should be agreed there, otherwise it's not true. Maybe by chasing a diagrams up, I maybe proved one direction, but one can see why the second direction is true. But okay, so this is important, really. We need to check this. So maybe let me give you an example, and then to say something about why this square, the left square, is weakly pullback, because it's so important. Otherwise, the lemma, it's not true. Example can help here. Let's take this. Okay, it's so known. This the PR box. It's even known that it's a contextual vertex, but this PR box. I mean here this scenario. I'm this scenario with delta Z2. I want to show that this PR box is non-contextual. Is contextual. Sorry. Using this lemma. I want here to take, okay, again 0, 0, and maybe I will take here the opposite. How we can see this? We can actually write this as we showed before, as a gluing of this, both of this. Okay, we glue to get this, okay, in these 2 points. So now by restricting what the lemma told me that let's restrict this to this side and this side, and show me, we should show that this is a property, and this is if and only if. So if we don't have like this, then it's contextual, right? I wrote, so let's see. Okay, yes. So I will show that it's contextual. So I want to show you that there is no something like this. There is no pre-image for this and for this that agree. Let's find all the pre-image for this part. We're restricting first of all to A, like let's say this part up. Now I want the pre-image of this, okay? Remove it like here. Okay. Want the pre-image. So one can check here actually that this coming from this distribution, like distribution like this. One can see this from the one, sorry. Like if I have this 0, 0, 0, this is a map. I mean, this is a map in here to delta of Z2, because it's defined by the vertices. And this is another map. So one can see that the only distribution that going to this is the only one that going to half. You understand what I mean? This is this one is here. Yeah, You understand? Like there is two map. What is something here is a distribution on the section here on the maps here. So this is a map, one map. Everyone get half. This is the only pre-image. Okay, one can check this. This will be good exercise. The only pre-image. Here I apply theta. Okay, I apply theta and get this. By applying theta, we get this. Similarly, for the other part, we have what we put here, this one. It's also something similar, that the only pre-image for this will be, like we have this, 0, 0, 1, and 1, 1, 0. Like everyone take half, this half going to half, this half. This is also the only pre-image by theta. Yeah. Same here, the only pre-image. So now, in order to check contextuality, according to the lemma, or they agree, the pre-image agrees on the restriction on the 2 point or not. That is the whole, yeah. So the only pre-image. So what is the restriction of the first one? To like let going here and doing restriction to by other color now. Restriction to D of 2 points delta Z 2. If we going by to restrict it, so one can see that this one will be the following distribution that I will write here. Maybe. One can see that the only thing that when you have 0 on both, you will get half. Sorry, 0 on both, it's half. And 1 in both, it's half. Yeah, one can see it's easily like this is the only way like you can, yeah, right? Because this is you restrict to. So okay, one can go to the definition of this and see. And for this one, again, the restriction, I mean, okay, I will not write it again, but one can see that this one, it's the only restriction is 1 here and 0 here. This will take half. This is distribution. What I explained is distribution. So this is a unique distribution in the, yeah. Because there is one unique here. The restriction of this is one distribution, right? Yeah. So 1 here, 1, 0. And we see it's not the same. Yeah. We see that here, this one and this one, not the same. So they are not agree. This one's not agree. So that means as from the lemma, we got that by the lemma, what called the gluing lemma, we call gluing lemma. This distribution that we have from the beginning. This is a PR box. It's not really that is even its extreme point. It's not that. It's not. It's contextual. We now proved it as exercise example for the gluing lemma is contextual. Okay, I want to if there is questions, but okay, let me finish and then we can get questions. Some last things I want just to say something about why the one I wrote here, it's what it was. It was like this. We have, I remember something like this. We wrote, no, something like this. We had in simplicial set this one, which is pushout. And then by applying a simplicial set only on this, it's known that this one will be pullback. This is known, okay? This is how we get that the pullback when we apply simply to dy. It's the same, okay? It doesn't matter what it's y or dy or anything. By applying this contravariant factor, we will get what is here, a y. We get the pullback. This is a pullback. But if we apply d on this, we take this and apply d on everything, it's not a pullback, but a weak pullback. This is what I want to explain. So what I want to explain that if we have now anything like, let me now use new letters. So if we have, what I can use new letter. Okay, UVW maybe, UVW in sets, because this is in sets. Okay, UVW M anyway, like this is in sets. If this is the pullback, then applying D on this will be weak pullback. Okay. So what it's mean a pullback? Like how it's look like this M, the pullback, it's U cross V W. Like every it's good to remember what it's the pullback. Like every member here, it's someone from V, someone from U, like pair like this, such that when we down, let's call it F and G, such that F of U is equal to G of V. This is what it means, a pullback, right? In 4 sets, this is a pullback 4 sets. And now, if we apply D, we will get that it's weak pullback, as I explained before. But why it's true? Because actually, like if we take the real pullback, like let's say we apply D on this. This will be a commutative diagram because D is a functor. But we have here a pullback for this, right? We have here the pullback of these ones. So D V D U D W. And we have a map. So because this is a pullback, so we have a unique map from here to here. There is a unique map induced by the diagram. In okay, maybe I will write it in black because it's induced by the diagram on black. Actually, what we prove that there is a section for this one. This is what we prove, that there is a section for this map. So this section actually, we have something like this. If you remember when we talked about convex category, the first one, the theoretical talk was the first talk. You remember I defined M like from when we have D, let's say V cross DU to DU VU, and with some property. So this can extend it to some M from when we have pullback, because okay, product is some special case of pullback, okay? And this have really some property. We told something about the property of this. We said something about the property of this, but this also have a little bit less properties, but some of them really is the same property. This will join us later. This is actually why I wanted to talk about this a little bit, because we will use this later, I think, in the talk when for homotopical characterization, this talk, and maybe also for bundles we need for this, for the category some properties. So it will be this is good to really to know that the distribution monad have this. Here it's wrong. What I want, right? It should be D for all. Yeah. It's have some property of composition, like it's look like because some of composition, right? Like here we have two and which agree on something, and then we compose and get something here. Okay, there's no time to talk about this, but we will leave it for next talks. We will need this again. That is, if there is questions, I will be happy.
Okay, thank you, Aziz.
Thank you, John.
Okay, questions? Okay, seems like there are no questions. So I guess for next time, Salman will take over from here and provide some applications, proof finds theorem, and it's
It will be on Monday, right?
Yeah, so actually,
by Zoom, right?
I don't think so, because you'll be here, right?
I will be there. Okay. Because actually, no, still I have something on next from there in Zoom in this time, but then only on next Sunday, on next Monday. But the next, okay, I will be free. You understand me? Yeah. So,
yeah, I see. So next Monday, you're not here, but we can still have it on in person here. Then I mean, just make a difference. So okay, I'll decide on that. So I'm not sure, because if I announce it in person and then decide to do also Zoom, then I need to set up the camera. But it's been a long time, so I have to remember the details. So yeah.
I don't know. I feel that that's changing too many variables. Maybe we just fix it. I don't know. What room will it be in? Seminar room?
Yeah, normally.
Okay.
But also I think
it's not now. It's not good. Yeah.
So, no, I mean I think it was. So I think Salman, you prepared the talk for Zoom, I guess, right? So this is maybe we can have it on,
I really don't care either way, but I just think that maybe it will be confusing.
No, I'll explain it in the email anyways. I mean, it's confusing now, but I'll fix one option. But yeah, so I think if it doesn't make any difference from the presentation perspective, I guess we can have it all in person on Monday. But the only difficulty is on my end, which is setting up the camera. So,
yeah.
Okay. Yes. Any other things to discuss? So I guess we know what the talk will be about next time, and I think the talk after that is probably yeah. So there's some flexibility there. I think I was planning to talk about the rank paper. Which includes twisting. I guess I can do that without introducing the bundle stuff. So
yeah, but the next talk will be the talk of Salman, right?